So let me just introduce you. So our next speaker is Professor Mykola Lysynskyi from Institute of Mathematics at Kiev Academic University. And the topic of his talk is a classification of smooth structures on line with two origins. Yes, please.
May I correct you? I am not a professor, but okay. I'm gonna start with definition of locally Euclidean spaces. First, the topological space is said to be locally Euclidean if for any point there exists an open embedding phi of some open neighborhood of X. We call this such embedding is called a chart. Um, we should say that M may vary depending on the point if our space is not connected. The collection of charts which covers the whole space is called an atlas. It's also often, such spaces are often called the topological manifolds if such charts are present. It is seen that often in definition of smooth manifolds, we must the space must be second countable. It must have it must be Hausdorff, but for definition of smooth structure, not all other properties which often are very helpful, we only need the locally Euclidean property. We say that if we have two charts on our manifold which intersects, then homomorphism from images of intersections of these charts we will call the transition map between these charts. We say that two charts are CK compatible if the corresponding transition map is CK differentiable in the multivariable calculus sense. Of the definition of these smooth structures, I refer to the John M. Lee, and instead of describing the maximum atlases, we will only consider the smallest atlases, because maximum atlases is good for some theorems, for some applications, but I think that they are too big to be observable in some sense. We say that on the manifold, on a topological space, on a locally Euclidean topological space, we have a CK structure if we have an atlas which consists of charts that either have CK differentiable transition maps or are empty. Their intersection are empty. First, I want to recall the well-known result of classification of smooth structures on Hausdorff 1 manifolds. For that, I will recall the definition of the joinable charts. So let we have two charts U and V on M, and they are said to be CK joinable if they are CK compatible, and the following condition is fulfilled. Thus, they are the same on the intersection, which is always can be achieved for two charts which are intersects, such that no one from the charts are fully inside the other chart, because we can introduce a new chart which consists of the previous chart with homomorphism with composition in the diffeomorphism. Thus, such conditions are almost can be achieved at least for one-dimensional case, because we here describing the one-dimensional case. Thus, we have the intervals. And we can see that A less than B, B less than C, C less than D, this is all real numbers. Also, the open inclusion map sigma from the union of these domains of these two charts and corresponding chart, which can be obtained such way, we will call the CK join of U and V. If W is CK compatible with U and V and differ only on the intersection. Essentially, we are just defining new chart, which is CK compatible with previous two charts, and the restriction of this homeomorphism is precisely these charts on the set u z minus v, or vice versa. Then another definition. Suppose we have a countable CK atlas on R, or any one-dimensional chart, one-dimensional manifold. Here I will refer to the theorem of Milnor that say that up to diffeomorphism for connected Hausdorff second countable one-dimensional manifolds are only R and circle S1. We will call atlas B is chain-like if for all integers the following condition holds. First, the charts Vj and Vj plus 1 are CK joinable, and essentially only two of charts may intersect. Thus we have some covering of R, which looks like a chain, from which we obtain such name. And shortly, the uniqueness of CK structures on R can be quite easily proved. We just utilize the induction. We join in, suppose, V0, a chart with V1 chart. Here, as we can see, V0 with V1. We obtain new chart. We call it sigma 0 or sigma 0, 1. Then we join this chart to V minus 1, etc. In the end, we obtain a single chart with single, I should say, by the construction, if we are going to details, sigma is also a diffeomorphism. And we obtain that essentially we can change, like construct a diffeomorphisms between any two spaces R with any two different atlases on it. Thus, it's only a one unique CK structure on R. Similarly, we can prove that there are unique CK structures on a circle. We even have a simpler case because the circle is compact. We can, as we can say, we can extract a finite subcovering. In this subcovering, we can construct a chain-like atlas, and then we can join, if we have n elements in our atlas, we can join n minus 1 elements. Then we obtain two charts, and it's a well-known result that two circles which two charts are CK compatible, we are CK diffeomorphic, which means that there exists a CK diffeomorphism between any two circles with different atlases. So I want to tell about line with two origins. What is its space actually? I will use such definition, but I recall, but I also will provide some another definition to introduce maybe yes, I will provide some other definitions. Let R tau be a real line with the standard topology, that is Euclidean topology. Then the joint union L of the R and point will be, we'll call this point 0 dashed, and out with topology eta, which is just the union of tau with neighborhoods of 0, in which we replace 0 with this point dash 0. We will, such space we will call each is said to be the line with two origins. This space also can be defined as quotient space of disjoint union of two copies of R, in which we make any points of except zeros are equivalent with each other. Or we can consider the foliation of the real plane by the parallel lines and exclude one point like 0. Then the supposed space of lines, if we try to parameterize of lines, there become exactly the line with two origins. So how we should describe the problem of classification of smooth structures on L? First, I should say how we can define the smooth structure. As you can see on this diagram, I draw only two charts. Essentially, it's chart psi, which contains 0, and chart phi, which contains 0 dashed. Phi is a homeomorphism, psi and the homeomorphism, but the domain of such charts are the all suppose if you consider this chart, we see that domain of this chart is L without this point. And same for phi, but we exclude other point. Why we can do that? Because essentially, if we exclude one of these points, we have the R, just a real line. And we can naturally essentially it's just a real lines. So by using the if consider we have a big atlas which consists of many charts which may intersect, which may some of which may not intersect, analogously to the case of one-dimensional Hausdorff case, we can construct an atlas which BCK compatible with previous atlas, but will consist only of two charts, and we call this atlas reduced. So we have a problem: how to define, how to classify all the smooth structures of L. To properly state it, we should define the orbits of action of group of homeomorphisms of L on the set of all CK structures on L. Because if we construct, if you have a smooth manifold with some CK structure, that is CK differentiable atlas, if you construct a homeomorphism of this space and apply this homeomorphism to all homeomorphisms in charts, we obtain that H will be not only homeomorphisms but diffeomorphism. Thus, we should only consider the orbits of such action. So first, let's define what I call the zero extension. So as we can see, by definition, our transition map should be CK differentiable in the calculus sense. But instead of, in contrast to the Hausdorff case, here we have that our transition map have a domain and codomain is R without 0. Thus, it's not a diffeomorphism of R, but instead it's a diffeomorphism of R without 0. And interestingly enough, that for as transition map should be a homeomorphism, we only should consider the monotonic case, that is the function 1 over x, in some sense, is a diffeomorphism of R without 0. But it is not continuous on the R. So we can, in some sense, identify every monotonic diffeomorphism, or essentially here it's a transition map, with a homeomorphism which preserves 0 and is the diffeomorphisms of R without 0. And such a map we will call a zero extension. So zero extension will be denoted as GA, where A is an atlas which represents the corresponding CK structure. I should remind.
Yes. So sorry. So you just define additionally you take this map psi in phi minus 1 and you define it at 0 to be 0, yes, and that's
Yes,
all.
yes. Because it's uniquely so. In order to be a homomorphisms, it's uniquely it should be defined zero in 0 to be 0, and all other cases will not be a homeomorphism. Then before stating the main theorem, I want to recall the definition of the double cosets. Let G be a group and K and H are two subgroups of G. Then for all G, the set of such form is said to be the KH coset of G. In particular, KH cosets form a partition of G, which is denoted in such manner. If K and H are equal, first property is that if we take the inverses of all elements in such coset, we obtain this coset. In other words, the inverse element. So if we have two elements, suppose it's if we have element G and its inverse, so the KK coset of G, then KG minus 1 K will also be a coset. And such union we will call the K plus minus double coset of G.
I'm sorry for interrupting you, just to say that you have less than 5 minutes left. I'm sorry.
Okay. I'll be a bit faster. Okay. So here we can see the examples of such partition for the dihedral group, and here is some small lemma for double cosets, which will be used in the next in the main theorem. So suppose A and B are a pair of reduced atlases on L, and GA and GB it's a corresponding zero extensions of transition maps of this in these atlases. Then following two correspondences, which establish a bijection between the set of diffeomorphisms of L which fix the points, which we call branched points, with fixed points, is each diffeomorphism which fix points is will be mapped to a intersection of group of diffeomorphism R which fix 0 with intersection of such set, that is GB times dr0 and GA to the power of minus 1. And more precisely, so each diffeomorphism of H, it's just the it is in the composition of its two charts. It is which we say is the local representation of map H in corresponding charts. And for if our diffeomorphism is exchanging points, the only difference is that this element is no longer inverse. This is a small detail, but essentially it means that in such case, if you have the same structure, here we are obtaining the conjugation, or in other words, inner automorphism. If you consider this group as a subgroup of group of homeomorphisms, which fixes 0, then this intersection is always a subgroup. So this is a short sketch of proof, so which we can we need to show this is such correspondence as a bijection, and since the image of U and V is the same, we have the local representations, which we denote A and B in the corresponding charts. The assumption that H is a CK diffeomorphisms, the CK diffeomorphism L is equivalent to saying that A and B are are diffeomorphisms of R which fixes 0. here by this equality we can see how A and B essentially are connected. By taking the zero extension of such diffeomorphism, we obtain here that B is equal to zero extension of the transition map in B, composition at A, the composition the inverse of zero extension of the transition map in A. But B is a diffeomorphism, thus B must lie in such intersection. Hence, this is a well-defined map. From the such equality, which can be deduced from this, we can construct the following mapping H. We can see that such formulas for H coincide on the intersection. Hence, H is continuous bijection. Furthermore, we obtain the following diagrams when we first restrict our H to the U and to the V. We obtain that local representation is essentially an A, and here local representation of H of the restriction is B, which shows that the local representation of local representation of H in charts U and V are CK diffeomorphisms A and B respectively. Therefore, H is a CK diffeomorphism between these two smooth structures on L. Thus, Xi fix AB is a bijection. So I come back to the.
I am sorry, the time is up. Maybe in a few words, if you can.
Yeah. I'm finished.
I'm sorry.
This is the last slide. The proof for this case is analogous. We just need to swap here from the U to V and here from V to U, and we obtain such map and such correspondence, and we've proved that this is also a bijections. So thank you. This is the end. Thank you for all who listened.
I would like to thank for the very nice and interesting talk.